Hi guys, today I want to talk to you about a circuit which is called which acts like an overcurrent protection. The idea is to use just NPN circuit because NPN topologies because in consumer electronics you want to save as much money as possible, and a transistor costs less than an op-amp. Yes, of course you could implement a system in which you have a shunt resistor, then with a differential amplifier like an INA converts the signal and just use a comparator with a Schmitt trigger if you want, which set a threshold TR, and when the threshold is reached, the PWM signal goes permanently to zero. You could do that if you want, but this guy here and this guy here cost much money than transistors. So in a mass-produced solution, you can let's say that you have to produce 10,000 million of circuits. This solution can cost €1 more than just few NPN transistor. So it is also interesting to look at the different solution, even though you know that it is very, very simple. So let's use a differential stage, a PNP differential stage. The PNP differential stage can be supplied with resistors or with current mirrors. I prefer current mirrors because they act as active loads, and so we will use a resistor from one side and a current mirror to the other side. Let's use the Darlington because it has more gain. It is more so it is more precise than the single one. So let's put a resistor of 47 kilo ohm and a supply of 5 ohms. 5 volts, sorry. I'm drunk. Okay. Thanks. Let's put a useless bypass capacitor because yes, this is useless. But let's put it anyway. It is useless in this simulation, okay? It is not useless than in real life. Let's put these guys to ground. And now let's polarize this differential stage with NPN circuit, with an NPN current mirror. You can even use the beta helper here. You can put it in a diode configuration like this, or put the beta helper like this. And connect it, of course, and this has to be connected to the power supply. But it is for this simulation we can omit that. Just use the classical. You can even use the cascode current mirror. There are a lot of current mirrors, by the way. I will make a video about current mirrors. I promise, because I like them a lot. Okay, so how does this circuit works? From one side, you have the measurement. And on the other side, you have the reference. Now, we want to set the reference with a divider, which also polarizes the base of this transistor here. So let's put a very low reference, like 51K and 1K. So this should be around 150 millivolts. Let's put also a capacitor to stabilize the reference of 1 micro. And now the idea is to take the output of the differential stage and to use a non-inverting level shifter. The easiest way to do a non-inverting level shifter is to use a double NPN pair. Again, you could even buy an integrated level shifter, but I think that the easiest way is to use a double NOR gate. A double NOT gate, sorry, like this, with 2 pull-up resistor, 1K and 1K. We then feed back the reference to the output of the non-inverting level shifter, and we put just a resistor here because we don't want to create shorts. So 100 kilo ohms is enough. And let's put all the mirrors to ground. So we need to test the circuit, and this will be the overcurrent pin. When the overcurrent goes to 0, it means that there is a high current in the circuit and the PWM needs to be shut down. So the only thing left to do is to put, for instance, a boost converter with a MOSFET. So let's use an NMOS. It is a low side NMOS. And let's use a gain of 5. And this will be our PWM signal. Let's use an input of 10 volts. And let's use a diode, I don't care, 22 micro. And let's put a very, very light load. Of 3 ohms. So this will be the output pin. Let's put a shunt. This will be out plus, and this will be out minus. Sorry, this is the opposite. Out plus and out minus. Because the current flows in this way, and so the drop will be in the other way around. Now, since it is a differential measurement, we need to take the gain, the single-ended, the differential measurement to a single-ended, like this. You know already how to do it. Okay, so now let's generate the PWM. We want to say that when the overcurrent occurs, the PWM goes to 0. The best way to do it is to put a PWM signal with an end. So let's put 1 MHz, 1, 0, 1 nano, 1 nano, 1 micro, and 2 micro. This is a 1 MHz PWM with 50% of duty cycle. And let's put the overcurrent inside this as an input, and the output will be the PWM. So let's run the simulation and let's see what happens. Okay, first, let's check the switching node. Okay, nothing new under the sun. Let's stop the simulation because I don't need this. So first, let's check the reference. The reference voltage is set to more or less 150 millivolts. And let's check the measurement. The measurement is under the overcurrent, so the overcurrent is 1. And since the overcurrent is 1, 1 and x is equal to x. So the PWM is okay. It goes inside the MOSFET, which is 0.5 volts, and it can switch. It will be more or less around 20 volts because the boost converter is set to 50%, so the output is the input times 2. And you see that more or less we are here. There is the drop of the diode in between, so we have more or less this time minus 0.7, and we are free to go. As you can see, it is exactly that. More or less, it is exactly that. Now let's use instead a step load between a ramp between 0 and 10, and the rest time is 1 milli. 5 milli, for instance, and the fall time is I don't care. Let's run the simulation and let's see what happens. So the pulse is increasing, the overcurrent is still on, the PWM is still on, but then, as you can see, at this point here, at 5 dot something, at 5 dot something, we have the overcurrent protection which is activated, and so the PWM goes to 0, and the circuit is and the MOSFET is permanently open. Meaning that the input is connected right to the output, and in the output voltage will be equal to the input voltage. Let's check if it's true, and of course it is true. We have this kind of ringing because the MOSFET is open and it is conducting with this body diode, and so we have basically the input voltage minus the diode 0.7 and a resonance of a non-damped LC circuit. And so you have something like this, 20 volts when the PWM is conducting, and then the overcurrent protection starts to kick off, and the boost converter goes down to the input voltage. So as you can see, it works. It works. Okay, it is done with NPNs. It is done with the NPN circuit. The design is a little bit more complicated because you need to provide current mirrors, good polarization, good bias, and you need to set correctly here the reference voltage. But once you do this, you obtain a very cheap circuit without any integrated circuit. So it is very good. You can even improve this circuit by putting another NPN here, which stands like this. This is called the beta helper and improves the performance of your current mirror. Again, I will do a video just for current mirrors. So let me run again the simulation with the beta helper this time. There shouldn't be any kind of differences because it is just the current mirror acts like the same. And as you can see, the result is exactly like before. Maybe the reference has changed a bit. Maybe. No, the reference is the same. The reference is the same. So the overcurrent goes to 0, the PWM goes to 0, and the input voltage goes to the output voltage goes equal to the input voltage. I think that we can close the video now. Thank you guys for your attention, and see you in the next video.